This is going to be an example from your book. It's going to be from section 2.4, and it's going to be just problem 1. And we're given an initial value problem. It's 2xy dx plus x squared minus 1 dy equal to 0. And we're given the initial condition, y of 2 is equal to 3. So before we start anything, we have to make sure that we're looking at an exact equation, sort of everything's in the form that we're used to, or maybe not used to at this point, but that our notes say it has to be. Oh no. X squared minus 1. Sorry, I accidentally turned off my screen and now it's not letting me draw. X squared minus 1 dy equal to 0. And now, up to now, we've said the thing attached to x is m, related to df dx, and the thing attached to y is n, related to df dy. So if I want to go ahead and check that it's exact, I need to take the derivative with respect to y of the thing attached to x, that's m, d dy of 2xy. And the derivative of 2xy with respect to y is just 2x. Remember how to take your partial derivatives for this section, it's important. And then we take the derivative with respect to x of the thing attached to y, that's n. So the derivative with respect to x of x squared minus 1. And the derivative of x squared minus 1 with respect to x is 2x. So those are the same. This is an exact equation. Those were, I think, steps 1 and 2. And then we're going to go ahead on, now that we know we can use this method, actually applying it by integrating a bunch of stuff. So remember, we kind of have in our mind that df dx is m, or 2xy, and df dy is n, or x squared minus 1. And so we're just trying to find that f right now. So I say, okay, I'm going to integrate m with respect to x. So that's the integral of 2xy with respect to x. So that's going to be x squared times y, plus something that I'm not really sure what it is, that only depends on y. And so it didn't appear in my derivative with respect to x. I couldn't recover it when I integrate with respect to x, and I have to find out that thing. So I'm going to say, okay, well, if since f is equal to x squared plus y plus g of, sorry, not x squared plus y, x squared times y plus g of y, I know that g of y is equal to f minus x squared times y. So my derivative, g prime of y, is equal to df dy minus the derivative of x squared y with respect to y is just x squared. And then my df dy is my n, so it's just x squared minus 1 minus x squared, or just minus 1. So if I want to find out what g of y is, I just need to integrate it with respect to y now. So it's the integral of g prime of y with respect to y, integral of -1 with respect to y. So just negative y. This thing right here, you don't have to write. I just wrote it so that you would understand why I'm taking this integral right now. And now I can go ahead and say I know f. So f was equal to this thing right here. So it was equal to x squared y plus g of y. But that's just negative y. And if I set that equal to a constant, then you can solve for y. So you can say, let's see, x squared minus 1 times y is equal to c, which means y is equal to c over x squared minus 1. That would give you the general solution to this problem, but this is an initial value problem, so that's not actually enough for us. So let's see. We know that the solution is y equal to c over x squared minus 1. And from here, it's just like any other differential equation that we turn into an initial value problem. So it's y of 2 equal to 3. So we want 3 is equal to c over 2 squared minus 1, equal to c over 4 minus 1 is 3. So 9 is what c would be. So the solution to the IVP is y is equal to 9 over x squared minus 1. And now we've done what the problem asked us to do, to solve an initial value problem. Now, I know that this kind of solving for f part can be a little bit tricky. So just remember, you need to keep track of f, its derivatives, m equal to df dx, and n equal to df dy, and solve for g of y in order to find your solution. So really just be careful and write everything down. To make sure that you don't lose things in your integration. So it's really easy in this first step to forget about g of y, and then you kind of think that you're done, and it's a surprisingly easy problem. So if you are working one of these problems and you don't solve for g, something went wrong. If you're working one of these problems and you don't set equal to a constant, you've done something wrong. Oops, you need, not Ned. You need the unknown constant at the end. And then if you can remember those things, this type of problem really does just boil down to integration that follows a very particular set of rules. So, hopefully that kind of helps you out. Next up, we're going to set up another example, I think. Yeah, we've got time for it. And the reason I'm just setting it up is because we're going to actually kind of have to learn something new in this section. So it's example number 45 from section 2.4. And what we're thinking about is just this problem of if you have kind of like a little pin, the hole available to you, and a chain attached to that pin, and your chain is kind of falling down with some velocity v, depending on how far it's fallen, a distance x. The differential equation for this process is xv dv dx plus v squared is equal to 32x. Describes a chain falling at speed v at its current length, or height or distance from the surface it started from, x. So this is going to be our application type problem. And I just wanted to kind of like write it out for you right here. And then in the next video, we'll talk about why we need an extra tool to actually solve it.